coming, everyone. This presentation is going to be, I'm actually going to focus more on setting up the scope and the things that I see people do wrong when they're assessing NDT techniques. The reason why is there's a lot more detail around the actual how-to in the paper. So you want to really get into the nuts and bolts of it and set up a system to assess NDT techniques, then I recommend you look at the paper for more detail. So the first thing you actually have to look at as an organisation is why you're actually looking to do NDT. Okay? It's the thing that people, it sort of comes up and the question's asked, why don't the NDT have polls? And people struggle to actually answer that question. So they go down the path of, okay, let's assess some NDT. But if you're actually going to put some numbers behind it, put some robust discussion behind it that you can use internally, you need to look at the average age of your network and your network age profile. And look, I'm going to be talking mainly about wood poles here. It is applicable to steel and concrete as well. Okay. So this is a typical age profile of a network. So the blue line there is the untreated DC1s, so durability class 1 timbers, and the average age of those is about 60 years old or 50 odd years old in that network. With a life expectancy, average life expectancy is 65, that's a fair chunk of the network. The yellow is the DC2s treated, and everything else is sort of scattered amongst all the other different pole types. So this utility's been using sound, dig and drill for a while, and that's great, but the poles haven't really got to the average age where they're going to start to fail. So you're not really getting an indication. If you're looking at it saying, okay, what we're doing is working at the moment, we're not getting that many failures, it's really just a matter of time. Okay? So when you look at it, if you keep doing what you're doing at the moment in terms of replacing the number of poles that you're currently replacing, you're going to end up with a very old network. This is due to the fact that after the Second World War, you were putting in multiple times more poles into the network than what you're replacing at the moment, or that you have been replacing for the last 20, 30 years. So there's a big differential between what you're replacing now and what you were putting in originally. So to avoid that, you have to bump up your replacement rates. That means cost. In this case, it would have meant tripling the cost of current replacement programs. And even then, you're still going to end up with some older poles in the network. So what you need to actually consider there is, okay, this is coming for everyone. How do we best address it in the most efficient way possible? And that's where NDT techniques come into it. It's actually more around making sure you're replacing poles that need to be replaced and not over-condemning. You will get more benefit out of that than it will cost you extra to do NDT. So to give you an idea also what the current inspectors are actually dealing with, if you're not using NDT in your network and you're just using sounding and visual, maybe a diameter measurement at ground line or something like that, this will give you an idea of what these guys are actually having to deal with. So I'll put it out there to the audience. What do you think this pole will actually break at? It's 345 mil diameter. It's got a design load of 8.5 kilonewtons. Original unfactored capacity was 11.6, which, by the way, probably shows that this pole was probably a little bit under designed to start with. But who thinks this? Hands up if you think this will go over 10 kilonewtons. Over 5 kilonewtons? Over 2 kilonewtons? Less than 2. Does that change your mind at all? So that's the top of the pole after failure, so that's hit the ground and split open. This pole does have spiral grain. That's the pole at the failure point after failure. So this is a shortened video of the actual test. This pole actually fails at about 3 kilonewtons. Okay? That's a 15.5 metre pole holding up a transmission line, and that's a pretty brittle fracture. Alternatively, this pole's a little bit bigger. Same species, same design mode. It's only maybe a kilometre down the road, and its original capacity would have been about 14.2. Who thinks this pole's going to go above 10 kilonewtons? Above 5 kilonewtons? Above 3 kilonewtons? So those that said above 10 kilonewtons would be wrong, but it was pretty close to that. This one actually breaks at 9.2 kilonewtons. The point is, visually, these two poles aren't that much different. In fact, this pole had a massive chunk of timber taken out of it that could have suggested that there wasn't more of an issue in there. Just about to go. Little pop there. You can see it's a lot more flexible than the other one too. Eventually she comes down. A lot of the times it's handy to know what comes back from the business in terms of when you propose NDT in your business, so that you can actually address that up front. The why not is a lot about this. It's not a problem for us at the moment. We're not getting pressure from anyone, so let's just ignore it for now. Okay? The other things that come back are the NDT techniques have to be 100% accurate. No technique's 100% accurate. It doesn't matter if you're dealing with steel, concrete, timber, fiberglass, it doesn't matter. No NDT technique is 100% accurate. You build a system around the results of that NDT system. NDT is actually quite economical when you look at it from a perspective of not having to pay 5, 10, 15, 250 grand to replace a pole that's still in good condition. Okay? Some NDT techniques are actually faster than standard techniques, so sound dig and drill type techniques, if the system's set up properly. And then large utilities they're naturally less innovative than small utilities. There's a whole heap of issues around change management and things like that, so they tend to just avoid it as much as possible. So what is the problem? The problem actually is figuring out where your worst case area is. Okay? It's a lot of people. I'll actually skip to this slide. That's a fairly typical diagram of how do you sound dig and drill a pole. Okay, 100 mil down, go down 45 degrees, put a scraper in, feel around, take a good wood measurement, and away you go. The problem is, where are you drilling in that cross section, and how are you defining where you're drilling in that cross section? Okay, and then you go to the point, well, okay, where am I going to drill vertically along the pole? And that's what we find when there's failures and there's court cases around failures. It's all about the ability to actually detect where the worst case was in that pole. That's where everything falls down. So basically, I just want to touch on good wood thickness for a little bit, because not a lot of people realise there's a lot of emphasis on it. It actually doesn't make a huge amount of difference to the end result. Okay? So if you've got 260mm diameter pole, which say an original factor of safety of 2.5, and you've got 50mm of good wood remaining, you've still got 86% of your strength, theoretically. 30mm of good wood, which is where most people cut off the, have a minimum good wood reading that will condemn a pole, you've still got 65% of your strength remaining. You go to 20mm good wood, you're still above a factor of safety of 1 using the old working stress terminology. You go to 15mm good wood, and that's when you start to get below a factor of safety of 1. Okay? 15mm of good wood is nothing. You're actually going to have more issues with section collapse than you will actual bending strength. Just to touch on it, compressive strength is actually quite effective as well. So it's actually more effective than bending strength. The benefit is timber's quite strong in compression and it never really makes a huge difference in pole failures. The more important factors are actually your loss of fibre strength in good wood. Okay? We know that timber will lose probably about 50% of its fibre strength over a 50-year life. Okay? Your design load, most poles are actually over-designed. Most timber would go in with a factor of safety of 6 or 8 when it's brand new. That's why timber has lasted as long as it has and has been so reliable. The question becomes, when you start to deal and look at steel and concrete, what is your limits that you have to put in for when you replace those poles, when you condemn them, because you don't have that fat built in to those designs. Okay? And that's why you get more cascade failures with steel and concrete poles as well. And your reduction in external diameter is actually way more critical than the internal diameter. So if you're looking at a 5mm radial loss, you've got still 89%, but it only takes you till 35mm radial loss on that diameter to have lost 60% of your strength and to be below a factor of safety of 1. So external diameter is critical, and measuring that is actually very critical to the overall results, even when you're using NDT techniques. So I'll just touch on the options quickly. Obviously, the option is still there to just not look at it. The problem with that option, it isn't a very good one because you're leaving yourself pretty well exposed. But essentially, the commercial, the safety regulator can come in, and you are really exposed for that. But the regulator's a little bit like Barrett. It's not quite. It's a bit hit and miss. They don't always get you. But the public, the shareholders, and directors of the company, they are the red foreman. They will come in and they won't miss you. Okay, you know where their foot's going. So the primary NDT options that are out there in terms of categories, you've got the seismic, vibration, modal analysis type techniques. You've got density meters, tomography, radar, proof loads. I'm not going to go into a huge amount of detail about them. The one thing I will say is resistance drilling is not an NDT technique. You are damaging that timber. You are putting a potential pathway for pathogens inside that timber, and you're potentially transferring pathogens between poles as well. But it's not an NDT technique. It's just a better way of drilling. Drilling isn't the problem. Okay? Sorry, drilling is your problem. That's what you want to move away from. So, coming to the actual testing of the NDT techniques, first step is define the status quo. Figure out what your current system is actually doing for you. What are its pitfalls? What are its benefits? What is the actual economic viability of your current system? Then basically you need to define the requirements for your new system. So what are you actually looking for? Are you looking for improved speed? Are you looking for less condemned poles? Are you looking for less failures, for instance? Once you define those first two, then you can do a desktop study around that criteria, and the paper has a lot more around the criteria in there, if you want to look into that. And then you do your desktop study, you narrow down the field of techniques that you want to look at, and then basically you go to the testing phase. And the testing phase involves two things. One, full-scale testing, so send inspection crews out, use experienced crews on each device. Don't try and put it in the hands of a guy that's never seen it before and get him to use it. Put them out there, test a couple of hundred poles if you can. The more the merrier. Then basically you need to set that up as well for repeatability and reproducibility. So repeatability, you have to be able to have the same guy come back to that same pole and get the same answer. Reproducibility is two different people have to go to that same pole with the same device and get the same answer. If you don't have that, you don't have an NDT device. You've just got a guesstimate machine. So you need to set up the test program around that. Once you've done that, there's actually the destructive testing itself, and you have to do destructive testing. You can't take the pole out of the field, cut it up, and know what that pole is going to break at. Most of these devices will actually give you an indication of whether they think that pole is under strength for its situation. Okay? So essentially, you need to measure against what that technology is actually measuring. So if you don't do the destructive testing to follow up with it, you will be wasting a lot of money. Okay? Because you can't use anything but that data to properly assess an NDT technique. To give you an example, hands up who thinks the pole on the left is the weaker one. Okay? Hands up those on the right. The pole on the right is actually half the strength of the pole on the left. And the reason is, that pole on the right is 100% decayed all the way through the cross section. Okay? Doesn't look like it, and when you cut that section, you can't tell unless you look at the shavings, unless you know what you're looking for. Okay? That's carried rod, complete cross section decay. And funnily enough, a sound dig and drill technique is really hard to detect that as well, because it's hard. It's hard on the surface, hard in compression, just weak in tension. One on the left, it's actually probably not far behind it. It's only about twice as strong in terms of the fibre strength. That one on the right had about 8 MPa, the one on the left had about 16 MPa for a 50 MPa original fibre strength. So you can't just cut poles up and then compare them to the results of NDT techniques. And by the way, this is applicable across all hardwoods. If anyone's using Australian hardwoods, it's also applicable across all pines. To give you an idea, the pole on the right, this is what it looked like in the field. And in the test rig, it really doesn't look that bad. There's nothing to say that it should do that. Just quickly on the test program itself, you've got full and refined. So full test program would basically be everything that the inspectors inspect, you pull it out of the ground and you break it all. That's going to give you the most data. There's no risk of missing poles, poles that may have failed, but none of the NDT techniques picked up on. So your road poles. It is very expensive though. Refined method is basically you take the results from all the inspections and you say, okay, which ones did they all agree on? And you just ignore them. You only pull out poles where there was disagreement between the devices that you're actually interested in moving forward with. That'll reduce your costs. There's a little bit of risk that you'll potentially, none of them picked up a road pole, but that risk is probably worth it for the cost savings. So, just in wrapping up, focus on the recommendations of the method itself, whether it be a red, amber, green type device, whether it gives you a risk rating, whether it gives you an SI rating, whether it gives you just an unserviceable, serviceable, urgent type result. know what it's telling you and assess it against that. Finally, if you take away one thing, don't give the task of reviewing NDT techniques to someone that has never looked at a pole or an NDT device before. That's probably one of the biggest cost stuff-ups that I've seen in the industry, is just giving a graduate engineer who's never looked at a pole sideways the task of actually assessing these things. Not that they're smart kids and stuff, it's just they've got such a learning curve. If you're going to take another two things away, assess the software recommendations, assess what comes out of that NDT device, and focus on the two R's, repeatability and reproducibility. If you've got those two, you can actually calibrate your inspection system around that. Okay?